Thank you for coming, or thank you for staying. I'm glad to see you back. We start today discussing vector spaces. It's the next chapter in the yellow book. I just realized that I haven't collected all of the tutorial questions which I have done in the past in relation to chapter 6 yet. I will do it in the next few days. That's right. So chapter 6, it's about vector spaces, and normally when we introduce vector spaces, we do it through axiomatic approach. So vector spaces, as you will see in a few moments, it's a set which is subject to a series of requirements, and like it or not, on a few occasions you will need to prove that you are able to recognize and test these requirements, or official name for these requirements is the axiom or axioms. So vector space, you will often see a combination like this. A vector space, it's a quadruple of symbols. So it's a set. V is a non-empty set. F in this quadruple represents one of the number systems, one of these three number systems: rational numbers, real numbers, or complex numbers. Plus and dot in this notation, it represents operations on a set. So plus, we use the symbol plus because it looks a lot like a regular plus on numbers. It's something which takes a couple of elements of V, you see, and returns another element of V. Dot operation, on the other hand, it takes one element of F, one element of V, and returns V. So you will see this object a lot in the yellow book, in the tutorial questions, in other places. It's a four objects. One of them is meant to be some set. Plus and dot represent some operations. Traditionally we call plus addition, dot we call scaling operation. Elements of V we're going to call vectors, even though many examples of such V, many examples of such quadruples, they will have nothing to do with the geometric term vector, and yet we're going to call them vectors. Elements of F, we're going to call them scalars. This is more in line with our understanding of the term scalars. So this is just a symbolic part of the business of vector spaces. More content-wise, like I said, we normally require from this quadruple to satisfy a few axioms or a few requirements. In fact, we have the whole lot of them, 10 requirements, 10 axioms, and you're supposed to know them, and you're supposed to be able to check them if you ask to. So here's the axioms you have to keep in mind, and those axioms, in a few questions in the yellow book, they will ask you to do that. If we have time today, I'll show you a few questions, one question today. So here they are, the axioms we expect from this quadruple in order to be able to call it a vector space. Here they are. First one says, whenever you add vectors, you will end up with the element in V. Implicitly, it is said already here. The plus operation takes couples of V elements into V elements. Second one, it looks like this. The formal writing of the second one looks like this. Essentially, it means that when you add things, you can ignore the order in which you add. You can ignore the brackets you put there. This one has a name actually, and that's a good thing to remember. This name we call it Associative Law of Addition. The third one says that when you add things, it's a typo actually here, it's supposed to be you. The third one says when you add things, you can add in any order You can add in any order, and that's the one which we call commutative law of addition. So if you're testing a particular set to be a vector space, this one must be checked as well. Fourth one says there must be in this set V you propose to be a vector space, or you're testing to be a vector space, there must be a special element which you call zero vector. And the distinguished property of this zero vector is this. Whenever you add this vector to any other element of your vector space, that doesn't change anything. That's the distinguished property of a zero. Fifth axiom says for any element in your space, I'm not sure if you're familiar with this symbol, which looks like a capital A flipped upside down. If you don't, this is just a symbol which abbreviates the prefix for any or for every. That's how you read this symbol. And I don't know if you saw this symbol before. This one is read. This one reads exists or there is. So the fifth axiom requires that any element, anyone in your proposed vector space, is supposed to have a negative. For any element, there must be a couple, a pair, which we normally denote by negative of that element, which works like this. If you add this element to the original one, you end up with a zero. It's the axiom which is called existence of a negative. Yeah, so this one called existence of a zero vector. And this one's called existence of negative vector. Yeah. Well, this one is the name which I have attached to this first one is called closed under addition. It's expectable name. We already discussed with you the idea of something being closed with respect to some operation. So this goes in line of that discussion. Right. 6.1. Altogether we have 10. 6.1 says if you scale a vector, you will end up with the element of the V. It's again, it's being closed with respect to scaling. And actually, in this particular line, I show you two different ways to write the scaling. I use dot here as a symbol which represents the scaling. But in fact, very often to save space and time and ink in your pen, you normally drop the dot and you just write them next to each other, and that works as well, as good as with the dot. So this is being closed under scaling. 7.1 looks like this. It says when you scale a vector a few times, you can scale instead only once, but with a multiple of coefficients. It's the one which deserves the name Associative Law of Scaling, because it looks a lot like this one. So it's again, it doesn't matter in which order you put the brackets in your scaling operation. 8.1 says, 8.1 specifies how the unity acts in scaling. When you scale something with a unity, you end up with the same element. Not too many left. The last two, the 9th and the 10th, they are the distributive laws. They resemble a lot the distributive laws with numbers. So 9 says when you scale an element with a sum, this is as good as scaling with the individual terms and then add after that. This one deserves a name scalar distributive law, because we're distributing the scalars in this case, right? I mean, the scalars from this bracket, they got distributed individually to the vector V. And the 10th one, it looks like this. It also looks like a distributive law, but this time we distribute vectors rather than scalars, so this one deserves the name vector distributive law. I draw your attention to this subtle thing for instance, in 9, in the axiom 9, even though I use this symbol plus here and here, these are different pluses. Even though the notation is identical, pluses here are totally different. On the left-hand side, you're adding numbers, the elements of F, which are either rationals, reals, or complex. Whereas on the right-hand side, this plus, it's the plus which is applied to vectors. It is this plus. If we had lots of symbols, strictly speaking and formally speaking, I should use different notations on the left and on the right-hand side for plus. It's just because we don't have so many symbols we get used to. That's why we use the same. But back in our heads, we have to make this distinction. It's a different pluses on the left-hand side and the right-hand side. This is not the case with 10. In 10, the pluses on the left and the right-hand side, they are identical because on both times you add vectors. So here in 10, on both occasions, plus is this plus. The one which is supposed to come with the vector space. Right. So notation, if you notes about the notations, in these axioms, I didn't say it beforehand, but I should have probably. The U, V, and W, these are the elements of V all the time. Greek letters, I follow the convention of Greek letters, they are the scalars, the elements of my F, which is either rational, reals, or complex. That's notation-wise. In the yellow book, actually, for vectors, for the elements of V, here, for this thing, they, rather than using this arrow above the letter, they use boldface. So in the yellow book, they just use this notation, or this convention, when they use the boldface for the vector symbols. Whereas on most of my slides, I stick to the arrow notation. I hope you can survive with that. I hope you can draw the connections between these two notations. When you will have your tutorials, most likely your tutors will use a third convention because they can't make a boldface on a blackboard with the chalk. Arrows not very popular with many of the tutors. I think so. So you will also see that some tutors, to emphasize boldface, some tutors to emphasize both, they just put the underline under the letter. So they will write something like this. If you see that, don't be confused. It's just a tutor's attempt to make a boldface appear on a blackboard with a piece of a chalk. So that's not a convention which you have to keep in mind, which is very often used by tutors and many other people. That's right. So I'll tell you honestly, most of the time verifying axioms, it's a boring exercise. So that's why you have to show your commitment and your ability to make a good structural presentation of a boring stuff. It's a skill, and my suspicion is that not many in this class actually possess that skill. The skill of making boring stuff look structural and understandable. Sorry. We're not going to torture you much with this, but a few times you have to show your ability to make this verification of all of the axioms. And there are a few questions in the yellow book which will give you the opportunity to practice. Most of the time there will be some shortcuts to avoid verification of all of the axioms, but like I said, on a few occasions you will need to do that. You have to suffer through it, and I hope you will suffer through it successfully. Any questions? I'll show you, well, we're done with this slide. On my next slide, I'll show you a few fundamental examples of the vector spaces. I'm not going to check all of the axioms for all of those examples. From the moment I show you those examples, we will assume that we know that these are the vector spaces. And then that will be a good point actually to reduce the work on many other examples in the yellow book. Any questions in relation to this slide, please? So there are plenty of examples of vector spaces. You can't really count all of them, but many of them come within the scope of a few fundamental examples, and that's the examples I'm going to discuss on this slide. So the most fundamental example you will see, and that will come under number 9 on my slide, it's the example of N Tuples. So symbol or notation-wise, that's the quadruple like this, where F as before. F is it will be always one of these three number systems: rationals, reals, or complex. So this symbol, f to the power n, it's the collection of n tuples. So it's a sequence of numbers, each of them n units long. So it's a sequence of n numbers. Every particular number comes from the f itself. Every particular number comes from f itself, and that's what the fn is. We call this n tuple, which comes from our language convention that we call pairs of numbers couples. We call triple of sequence of three numbers triples. We call sequence of four numbers quadruples. Sequence of five numbers quintuples, and so on. So for the n, we just use the name n tuple. This is the object. That's the most fundamental example of the vector space. That's the example where you can test all of your suspicions. Yes, all of your theories, wrong or correct ones about the vector spaces. I need to define what the plus and dot will be in case of n tuples. In case of n tuples, plus and dot is something which is done in a per component way. So if you have two n tuples, one of them I call x right here, the other one I call y right here, and that's a typical convention. You use the letter, say x, in the boldface or with the arrow to denote the sequence where every element is also used the letter x, but now we use the subscript to index them. So when you add them, you just define the addition by doing addition in a per component way. You see, I add the first component, I add the second component, I add all the way through, I add the last component. Scaling, defined similarly, you just define it in the per component way. Again, I draw your attention to the fact that even though I use plus, for instance, in this line, I use plus on the left and on the right hand side, these are different pluses. This is a plus which is being defined right now, the one which needs to be present in order to call something a vector space. And this is a plus between the numbers, which we know very well how it works. The only reason we use the same symbol because we don't have too much symbols. We can't really waste them around for every new thing we introduce. Instead, we have to make an effort here in our heads to keep in mind that the plus, even though it's the same symbol, it may mean different things. The same story with the dot here, with the scaling. This is a scaling of vectors, which is needed to be defined in order to call something a vector space. This is dots, which here, this is a regular multiplication between numbers. Lambda here is the element of my f, because I'm scaling with the f. Sometimes f is called field of scalars. I don't know if you know this term. I told you that the elements of f, we call them scalars. The whole set, cumulatively, we call it field of scalars, and that's why f, actually. It's the official name. Right, and that's the example. At this stage, I just showed you the example. From this moment on, I will rely on the fact that this is a vector space. And when I say that, in this little sentence, when I say this is a vector space, I assume that all of the 10 axioms I just listed to you, they all completely satisfied by this construction. And that's the first fundamental example of the vector space. Second fundamental example of the vector space you will see throughout the yellow book. This one, the most often appears the most often in the yellow book, and derivatives of this example appears the most often in the yellow book. The second example, which in the order of frequency of appearance in the yellow book, well, notation-wise, notation-wise, when F is taken, particularly Q or R or C, you will see these notations, and that is exactly what stands here, where you replace F with a C, with a Q, R, or C. Now to the second example, which appears often in the yellow book. It's a symbol like this. Again, it will be a few examples depending which F you choose, which field of scalars you choose. This is the set itself. The set itself, it's a collection of matrices, and we need to discuss now notations we often use to denote matrices. Here's a free notations we often use to denote matrices. If I want to write up a matrix, and the matrix, I hope you know, it's a table of numbers, rectangular table of numbers, I should say, with two dimensions, number of rows and number of columns. In these notations, the first index, in this notation, the first index represents the number of rows. It's a convention we're not going to change ever. And the second index represents the number of columns. So it's a collection of all matrices of size m times n. And notation-wise, these matrices are, that's what I'm going to use to denote the matrices. It's either little a, well, it may be some other letter, B, C, or any other letter, double indexed in brackets. This is already tells you that you're looking at the matrix, even though this notation doesn't specify the dimension of that matrix. This is a longer notation, which specifies the common symbol of the matrix, again double indexed, and it specifies the dimension of that matrix. J, the first index for row, K, the second index for columns, and this is the largest possible way to write up a matrix when you explicitly specify the elements and the indexing structure. Each of these notations will be used often throughout our joint meetings in the yellow book and even in the other topics. You have to get used to them. Writing-wise, this is the shortest one. Writing-wise, this is the shortest one, but it delivers the least amount of the information because it doesn't specify the size of the matrix. This is the best one, in my opinion, because it's short and yet it gives you the best amount of the information, but it doesn't actually expose explicitly the structure, whereas this one, of course, fully exposed, but it takes a lot to write this. So you're free to use combinations. In fact, it's another skill of being able to use these different notations in the right place in the right time in order to keep your writing short and yet understandable. And again, my skeptical side believes that not many in this class will ever manage that skill. But we'll try. We'll try. Anyway, this is notation-wise how we denote matrices. Now back to the vector spaces. All the matrices together. So this symbol, capital M, subindex Mn, and the field inside, it represents the class of all matrices, collection of all matrices, if you wish, such that the entries come from the chosen field of scalars. Now you understand this symbol completely. There shouldn't be anything mysterious about this symbol. Symbol stands for the collection of all matrices with a particular chosen field of scalars, particular chosen field which is used to fill in the entries of those matrices. Now this set can be converted into a vector space. In order to do that, I need to show you how we plus and how we scale matrices. And that's how we do it. Very similar to the way we do it with vectors. We do it in entry-wise way. And that's a good way to write this. Look at this. If I have two matrices, matrix A, capital A, it's a short way to write the matrix. And even though originally I said this one doesn't deliver all of the information, in the current context, when you write something like this, everything is written up, even though the size of the matrix is not exposed here. It is exposed in this part of the writing. So actually that's a very good choice to write of a notation. It's the shortest one, and yet you didn't lose any information. So if I have two matrices, A and B, I add them by doing the operation component-wise here. If I want to scale my matrices, if I want to scale my matrix, I'm sorry, you scale only one matrix. Again, you do scaling component-wise. Again, I draw your attention to the fact that the plus here and the plus here, they are totally different pluses. One of them is a plus on matrices. The other one is a plus between numbers. And these two pluses, they are different from this plus, which was plus on vectors. You see, one symbol plus on this slide has three different meanings right now. And it's your job to be able to make this decision, which meaning exactly plus represents on every particular occasion. The same story with the scaling. This scaling is different from this scaling, and it is different from this scaling, even though notation is the same. Like I said with the vectors, from this moment on, I will rely on the fact that this object is a vector space. So all of the 10 axioms I listed before, they are satisfied for this vector space. And now, many examples in the yellow book will be a derivative of this example. The way it will be derivatives, I'll explain next time. Any questions about these two examples? Okay, this is not all. There are basically three other examples, fundamental examples, which are very ubiquitous across the yellow book. Well, notation-wise, you will see this. When you choose a particular choice for F, when you make a particular choice, for F, matrices with the rational entries, matrices with real number entries, matrices with the complex number entries. It's just a notation where when you choose particular field for F in here. So third example, the notation I'm going to use, it's a little bit unconventional because actually we don't have a conventional notation for this. And the third example, it will be like a template example, which by itself it's not going to manifest itself too much in a yellow book, but I'll show you two derivatives of this example. So I chose this way to write this. I use the letter V to make a presentation of this example. This is less conventional than this notation, than M. So what are the elements here? A, B are two numbers. So basically this is an interval on the real line, A, B real numbers. This set itself, it's a collection of all functions defined on interval AB with values in a particular field. It's a huge set actually. It's a very huge set. I mean, if you take all of the functions, all possible functions on an interval with the values even in rationals, it will be a huge set. In fact, mathematicians never attempted to study that set in the way it is. It's more like a container for smaller sets which are most suitable for study. This is a huge set. And that's the only reason I presented it as a container, because within this set there will be more manageable sets, which you will see a lot through the yellow book. But still, it's a vector space if you define your operations properly. If you define this plus and dot, and this time we will need a fourth meaning for the plus and dot, isn't it? We had one meaning plus and dot for numbers. We had one meaning plus and dot for vectors, for N Tuples, for N Tuples. We had one meaning for plus and dot for matrices, and there will be another meaning, the fourth one in a row on one slide, for plus and dot for functions. So here's the meaning. Again, it's not that hard to understand that meaning. It's the one. So if I have two elements, if I have two functions, f and g, if I have two functions f and g from my set of all functions defined on the interval AB, I produce a new element, which I'm calling f plus g, and function-wise, it is defined as a point-wise addition of the function f of the function value f of x and the function value g of x. Scaling, same story. It's a point. Point-wise scaling. I'm sorry. It's a point-wise scaling. Like it or not, that's the fourth different meaning for the same symbol plus and the same symbol dot on the same on one particular slide. Yeah. Again, from this moment on, I will rely, and you can rely, on the fact that this is a vector space. All of the 10 axioms are satisfied. We actually, in this one slide, we're covering a huge amount of routine tasks right now. If you do it like in full detail, verification of all of these axioms for these examples, it will take a lot of space. You will do it, not for all of them, but a few times you will do it in the course of your solution of problems from the yellow book. You have to do it in order to get the grasp of it, and your tutor will help you when you have the tutorials. But 1 or 2 times will be more than enough for you to get the idea what's going on. Like I said, this is a container example. Within this example, we have more manageable examples, and here there are 2 of them left on this slide. I call it 3a. It's like a sub-example of example 3. That's a symbol we're going to use for that, PNF. PNF. This is a collection of all polynomials of degree n. It's a collection of all polynomials of degree n whose coefficients, or which coefficients, I'm sorry, come from a particular field f. Because polynomials, you can regard polynomials as functions, right? Nothing wrong with that. Polynomials are functions. They take elements of real, if your x here, if you treat your x as a real number, it's a function. It's a function defined in the whole real line. This class, you can think of it as a subspace in this example, where interval is replaced with real numbers, and this is a typo. This is supposed to be R. You can't put here F. You can't put here F because if your F even rationals, when you replace R with real numbers, your polynomial value will ultimately may be a real number, not necessarily a rational number. That's why you have to R here. But from the perspective of the example, all we need to know that this object with these operations, it's a vector space. It's another fact I'm going to rely on. Yeah. You can take coefficients reals, you can take coefficient rationals, you can take coefficients complex. It will be 3 examples of a vector space. Again, this will be something which satisfies all of the 10 axioms, and we'll leave verification of that on the side. Last example. Last canonical example you have to keep in mind all the time. It's again within the scope of this larger container example, class of all functions defined on interval AB. And that's this one already. It's a very conventional. This is a standard notation for this example. CAB. I'm not sure if you're familiar with this symbol. The symbol like this, you read it subset. So this is an example which will be a subset of all functions defined on the interval AB with values in R with a particular, you see R here, there's no exception here. And symbol itself means that function f is continuous. So this example, in short, this is a collection of all functions, or set of all functions defined on AB, which are continuous. which are continuous. I hope you understand why we excluded the rational set, rational part from it, because there's no functions, there's no continuous functions with rational values, isn't it? Or there is. When you study, if you think about that, that's the beauty of the real numbers on the top of the rational numbers, is that the real numbers, they represent the continuous structure, unlike rational. So you cannot possibly construct a function which takes only rational values and which is continuous at the same time. Continuous the way it is defined in calculus. That's why for this class we cannot take R here. Oh, sorry, Q here, Q. The smallest class we can take is R. That's the smallest class of numbers which admits continuity, which accepts continuity. And another notation which you need to remember, C sub C, it is basically the same as this. The only difference is that you take a continuous functions with values in complex numbers now, rather than real numbers. And we basically, that's all. That's a complete list of canonical examples which go for the yellow book, and you will see in the yellow book. I don't think you can come up with, I don't think in the yellow book you have any other fundamental examples of the vector space beside this, how many, 5, isn't it? In fact, like I said, this one, it's more like a container example. So this, instead you will see a lot of these two, either polynomials or a class of continuous functions. It doesn't mean there isn't any other vector spaces. There are plenty of the examples of the vector spaces within these 5, which sort of are derivatives of these 5. In which sense they are derivatives, we will discuss next time. There are also plenty of the examples beyond these 5, but they go, in order to study those examples, you will need significantly larger baggage of mathematics behind your shoulders. In fact, even this example of continuous functions, even though you will see a few examples in the yellow book which rely on this, even studying this example requires significantly more knowledge than you will ever master in this topic. But yeah, any questions? It's not an easy stuff actually, but you're taking it well. I like it. Thank you. I have one slide left, which is, like I said, all of these examples we had together, all of these examples we just discussed with you. From now on, we will rely on the fact that they are vector spaces and they satisfy all of the 10 axioms. But I need to comment a little bit on the way you verify the axioms. I will comment on this exactly on my next slide. I'll do it once. We have 10 minutes left, and I know it's the second hour through the mathematics lecture, so it should be, it will be a little bit, it may be a little bit difficult for you, but I hope we will survive. And I'll try to explain to you how to expose structure as much as what's actually the content you need to present when you verify axioms. It's not like you have to say a lot. I know sometimes, especially people in finance, they tend to say a lot and yet deliver zero content. You see, yeah, well, what are you laughing about? I think it's a part of the job description when you apply for the finance position anyway. Just open the morning show and listen to the guy which just discuss the stock market every morning. He says a lot, but basically he delivers zero information, isn't it? That's the part of the finance degree, I think, to be able to do that. Unlike that, when you verify axioms, we expect quite different in mathematics. We expect to say the least, but deliver maximum of content. It's quite opposite to what you see in finance. So here's the example I'd like to discuss with you. There will be 3 parts in this example, A, B, and C. We need to show that here's a 3 quadruples we're going to look at. All of them are N tuples. This is an N tuple of complex numbers. This is N tuple of complex numbers. This is N tuple of real numbers. all these three pluses on all of these three dots, they represent the plus and dot on N tuples. But you see the field, I'm playing around with this field. In the first occasion, it's just C. On the second occasion, it is R, even though it's N tuples of complex numbers. I'm going to scale them with real numbers. And on this occasion, it is C, but we're scaling N tuples of real numbers. We need to see that this, I need to convince you that this is a vector space, this is a vector space, and in fact, this is not a vector space. This is a part, in fact, this is a tutorial question 6. I mean, it's a question 6 in chapter 6 of Yellow Book. And I coupled it with this. This is a canonical one, canonical example we just done on the previous slide. That's why you can abbreviate this by one single CN writing. You cannot abbreviate this too by this writing, because this single writing, it assumes that the field of scalars is C. You cannot abbreviate this. You cannot abbreviate this example with this symbol, because this writing assumes that here is R, not C. That's why in these two parts, the only way to write is make the explicit quadruple writing. Whereas here we can do the abbreviation, of course, because that fits into the canonical scheme. That fits into the canonical scheme. So I'll check a few axioms, and I'll show you which axioms. I'll show you a few axioms which are failed in the C case. So in my verification, I will fix the notations. So U will represent, U with arrow will represent the N tuple of U's. V with arrow represents the N tuple of V's. And W with arrow represents the N tuple of W's. So I will check the axioms. Some of them are very routine. For instance, the first one says, the first one was, if you remember, your set's supposed to be closed under addition. So that's what I say here. If I want to make a concise but yet structural incomplete presentation for the axiom 1, that's what I say. I say that if I add two N tuples, U and V in this case, that's the resulting N tuple I'm going to be looking at. And now I need to convince you that if I add these two, I will end up in the same space. In case A and B, in these two cases, elements U, V, U, V, U, V, they come from complex numbers. And that's why if I add them, the result will be a complex number. And that's why every component in this resulting N tuple is a complex number. And that's why we have a closedness with respect to addition. In case of C, the shortest writing will be similar, but now we just use R instead of C, because in case of C, your N tuple is with real number components. When you add them, the sum will also be a real number component. And normally when you do this short way of writing things, when you use the J for the index, it is good practice when you indicate the range for J. We'll just try another routine one. Second one is the Associative Law of Addition. What's the time? We have 5 minutes. That's good. I'll show you one extra routine one. Okay. So it's the longest one to check. It's the longest one to write. And yet, even in this longest one, you can show some structure, and you show your ability to write things in a structural way. So if you look at the second axiom, there are two sides, left and the right-hand side. That's the left-hand side. When I add my U, V, and W vectors, in this order, U and V first and W second. Because I do operations in a per component way, I do the same with the components, but you see I expose this structure, I keep the brackets here as they are, in here. That's a complete exposure with the brackets kept intact. Now for the right-hand side, that's the writing for the right-hand side. Again, because my operations are done in a per component way, I do this in a per component way, but I keep the structure. You see, I keep the structure of the brackets on the right-hand side to make some distinction from the left-hand side computation. And now I say what I kept saying for the whole lecture. Because we have different pluses, these are the pluses on my N tuples. Whereas this plus and all of these pluses on the right-hand side, these are numerical pluses. Because we add, well, either complex numbers or real numbers, depending on the case here, but still these are numerical pluses. For the numerical pluses, we do know that the addition is associative. We do know this. So we can say that for the numerical pluses, we have this identity. And again, it's a good practice to indicate the range for J, if you use J to abbreviate your writings. And that's why this long expression equals to this long expression, because of this identity between numbers and numerical plus. Every time you verify an axiom, you have to make it very clear what your argument is, what's the sort of background knowledge you involving in your argument. In this particular argument for the second axiom, the background knowledge is this: the N tuple addition is associative because numerical addition is associative. So the background knowledge we employ is the fact that the addition for numbers is associative. You cannot make things from scratch in mathematics. You always rely on something in the background. And it's your job as a person who writes the argument to make this background very clear. Which background are you using? In this case, we use the background knowledge that the addition for numbers is associative. And that will be the case with all of the other routine axioms. You have to make this exposure. Which knowledge you use from the past. Well, 1 minute left. I'll show you why exactly this one fails. I mean, for the rest of the axioms, I hope I convey you the general idea. I will upload the complete site with every part open, and you will be able to see that if you are unable to recover the details by yourself. But I'll show you one in the remaining minute. I'll show you why C is not a vector space. Where is this, I wonder? Here. It's the axiom number 6, which fails. We're almost there. We're almost there. Excuse me, guys. I still have 1 minute of your time, and we're almost there. I know it's tough, but you're doing very well. Thank you very much. But we're almost there. I just show you one little axiom which fails in the case of B, and you will be free to go. So the axiom 6, if you remember, it says that the set must be closed under scaling, and that's where you failed it, because here's my three cases. Let me just open the whole thing, because the time is running out. That's what happens in the sixth axiom, when you need to check that your N tuples are closed under scaling. In the canonical case, your components are complex numbers, and you're scaling with the complex numbers. That's why components of the result will be complex numbers. In the B case, you're scaling with real number, and the components are complex numbers, and that's why components will be complex numbers, and that's allowed. In the C case, that's where you have the problem, because your components are reals, you're scaling with complex numbers, and you may end up with the complex number here, but you only allowed real components in the C case, and that's why your C case is not closed under scaling, and that's why the C case is not a vector space. Thank you very much for your patience. We're done today.